All right, so today we're talking about ARP, and I know what you're probably thinking. Another networking acronym to memorize. But honestly, ARP is one of those things that once you get it, networking suddenly makes way more sense. It's like finding the missing piece of a puzzle you've been stuck on. ARP stands for Address Resolution Protocol. The name actually tells you what it does. It resolves addresses. But what does that even mean? Well, think about it this way. Your computer knows IP addresses. It understands 192.168.1.5 or 10.0.0.20. But here's the thing. When data actually moves through your local network, it doesn't use IP addresses to get from one device to another. It uses MAC addresses, which are these physical addresses burned into your network card. So you've got this problem. Your computer knows where it wants to send data based on IP addresses, but the actual hardware needs MAC addresses to make it happen. That gap? That's what ARP fills in. So let's break this down step by step, because once you see how it works, you'll understand why every device on your network needs this protocol running in the background. The basic problem. ARP solves. Imagine you're sitting at your computer and you want to send a message to another computer on your local network. Maybe you're accessing a shared folder on someone else's machine, or you're printing something to a network printer. Your computer knows the IP address of that device. Maybe you typed it in, maybe it came from DNS, doesn't matter. Point is, you've got the IP address. But here's where things get tricky. Your switch, the thing that actually connects all your devices together, operates at what we call layer 2 of the networking model. And layer 2 devices don't care about IP addresses. They only understand MAC addresses. So even though your computer knows the IP address of where the data needs to go, it can't just hand that to the switch and call it a day. It needs to figure out the corresponding MAC address first, and that's exactly what ARP does. How ARP works. A simple example. Let's set up a scenario. You've got 4 computers connected to a switch. We'll call them host A, host B, host C, and host D. Each one has an IP address. Host A, 192.168.0.1. Host B, 192.168.0.2. Host C, 192.168.0.3. Host D, 192.168.0.4. Now host A wants to send data to host D. It knows host D's IP address, 192.168.0.4, but it doesn't know the MAC address. So what does it do? Host A basically shouts out to everyone on the network, hey, whoever has the IP address 192.168.0.4, tell me your MAC address. This message is sent as a broadcast. And in networking terms, a broadcast means it goes to every single device on the network. The way this works is a destination MAC address in the frame is set to all Fs, F, F, colon, 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 F, F. The switch sees this and forwards the message out every port except the one it came in on. So now host B, host C, and host D all receive this message. Host B looks at it and goes, 192.168.0.4? That's not me, and tosses it. Host C does the same thing, but when host D sees it, it realizes, oh, that's my IP address, this message is for me. So host D sends a reply directly back to host A. Not a broadcast this time, just a direct one-tune communication called a unicast. The reply says, hey, my IP address is 192.168.0.4 and my MAC address is this. Now, host A has what it needs. It knows the MAC address that corresponds to 192.168.0.4 and it can start sending data. The ARP cache. Making things faster. Now, you might be wondering, does this happen every single time a device wants to talk to another device? That would be exhausting, right? Constantly broadcasting requests, waiting for replies? Luckily, no. Once a device learns a MAC address through ARP, it stores that information in something called the ARP cache. Think of the ARP cache as a little cheat sheet your computer keeps. It's a table that lists IP addresses alongside their corresponding MAC addresses. So the next time host A wants to talk to host D, it doesn't need to send another broadcast. It just checks the ARP cache, finds the MAC address, and uses it. Problem solved. But these entries don't last forever. After a certain amount of time, usually a couple of minutes, that entries expire and get deleted. This is actually a good thing because devices can change. Maybe someone swaps out a network card or a different device gets assigned that IP address. By refreshing the cache periodically, ARP makes sure the information stays accurate. Seeing ARP in action. Let's actually look at this on a real computer. If you're on Windows, you can open up PowerShell or Command Prompt and type in a simple command, ARPA. This will show you the current ARP cache on your machine. When you run that command, you'll see a list of IP addresses, their corresponding MAC addresses, and the type, either dynamic or static. Dynamic entries are the ones your computer learned through ARP. Static entries are manually configured and don't expire. You'll also notice a few entries that are there by default. One of them is the broadcast address. You can spot it because its MAC address is all Fs. Then there are some multicast addresses which you can recognize because the MAC address starts with specific characters. Now, let's say you want to see ARP in action. Pick an IP address on your network and delete its entry from the cache. You can do this with the command ARPD followed by the IP address. Once it's gone, if you ping that IP address, your computer will have to send out an ARP request again. If you really want to get into the details, you can use a program like Wireshark to capture the network traffic. Start a capture, delete an ARP entry, and then ping that device. Stop the capture and filter by ARP. You'll see the whole conversation. Your computer broadcasting the ARP request and the other device sending back the reply. It's actually pretty cool to watch. When things get more complicated, talking outside your network. Alright, so we've covered how ARP works when two devices are on the same local network. But what happens when you need to communicate with something outside your network? Like, say you're trying to reach a website on the internet. That website doesn't have a MAC address you can find with ARP, right? It's not sitting on your local switch. This is where things get a bit more interesting. Let's say host A wants to reach a web server with the IP address 10.10.10.10. Host A has its own IP address, something like 192.168.0.1. It compares these two addresses and realizes, wait a second, that web server is not on my network. So what does it do? Well, every device on a network is configured with something called a default gateway. The default gateway is basically the router that connects your local network to the outside world. It's like the door out of your neighborhood. If you need to go somewhere that's not local, you go through the gateway. So instead of trying to ARP for the web server's MAC address, host A sends an ARP request for the default gateway. Let's say the gateway's IP address is 192.168.0.254. Host A broadcasts, who has 192.168.0.254? Tell me your MAC address. The router receives this, responds with its MAC address, and now host A can send its data. But here's the important part. The data frame that host A sends will have the router's MAC address as the destination, but the IP address inside will still be for the web server. The router's job is to take that packet, strip off the local network information, and forward it along toward the actual destination. The router handles all the heavy lifting from there. This is a key concept. ARP only works within a single layer 2 network, basically within the reach of a switch. Once you need to cross into another network, you rely on routers and default gateways. But even then, ARP is still involved in getting your data to the router in the first place. Different scenarios ARP handles. There are actually a few different situations where ARP comes into play. 1. Host to host. This is the basic scenario we covered first. One computer wants to talk to another on the same network. 2. Host to router. A computer needs to send data outside the network, so it uses ARP to find the MAC address of its default gateway. 3. Router to host. When a router receives data destined for a device on a local network, it uses ARP to find that device's MAC address. 4. Router to router. Routers can also use ARP to communicate with each other when they're on the same network segment. In all these cases, the process is the same. Broadcast a request, get a unicast reply, store the result in the cache. A quick look at the ARP header. For those of you studying for exams or just want to understand the technical details, let's talk about what's actually inside an ARP message. The ARP header has several fields: hardware type, This tells you what kind of network hardware is being used. For Ethernet, the value is 1. Protocol. Type. This indicates the network layer protocol. For IPv4, it's set to 0x0800 in hexadecimal. Hardware length. This is the length of the mask address. For Ethernet, it's 6 bytes. Protocol length. This is the length of the IP address. For IPv4, it's 4 bytes. Operation. This tells you whether the message is a request or a reply. A value of 1 means request, 2 means reply. Sender hardware address. The MAC address of the device sending the ARP message. Sender protocol address. The IP address of the sender. Target hardware address. The MAC address of the target device. In a request, this is usually set to all zeros or all Fs because the sender doesn't know it yet. Target protocol address, the IP address of the target device. When you see an ARP request, the target hardware address field will be empty or filled with zeros, because that's literally what the sender is trying to find out. In the reply, that field gets filled in with the actual MAC address. Why ARP matters. You might be wondering, why go through all this trouble? Why not just use IP addresses for everything? Well, the reason has to do with how networks are designed. The separation between layer 2, data link layer, and layer 3, network layer, allows for flexibility. Switches handle local traffic efficiently using MAC addresses, and routers handle the bigger picture of moving data between networks using IP addresses. ARP is the glue that makes these two layers work together. Without ARP, your computer wouldn't be able to send data to the right physical device. It would know where the data needs to go in theory, but it wouldn't have the actual hardware address needed to make it happen. So even though ARP works quietly in the background, it's absolutely essential. Wrapping up. So that's ARP. It's a simple protocol with a really important job. Translating IP addresses into MAC addresses so your data can actually move through your local network. The process is straightforward. Broadcast a request, get a unicast reply, cache the result for later use. Whether you're communicating with another computer on your network or sending data through a router to reach the internet, ARP is involved somewhere along the way. Understanding ARP gives you a much clearer picture of how networking actually works at a low level. It's one of those foundational concepts that, once you really get it, makes everything else easier to understand. And honestly, that's what networking is all about. A bunch of clever protocols working together to move data from point A to point B as efficiently as possible. If you found this helpful, go ahead and give it a like. Drop a comment if you've got questions or if there's another networking topic you'd like me to cover. And if you're not subscribed yet, hit that button. There's a lot more content like this coming your way. Thanks for sticking around, and I'll catch you in the next one.